Hello everybody and welcome to Blue Marble Science. Let's take a look at cherry picking the flat earth way. And who better to bring that to you than John the Quantum Eraser, Flat Earth's chief scientist. Warning: severe facial and monitor damage alert is in effect. Get out the oven mitts, push the monitors back out of punching range. Let's light this dumpster fire and have some fun. Recently my friend Bob the Science Guy did a video on Quantum Eraser and the way QE goes about cherry picking his citations. I thought it might be interesting to do something similar with QE's mental gymnastics concerning gas pressure and atmospheric pressure. So sit back and relax, and let's see how quickly we can take QE's own references and totally debunk everything he's saying.
Behavior. From the chemistry department at Purdue University, particles in a gas vibrate and move freely randomly at high speeds.
Well, yeah, QE, we know that. You didn't really need a citation, did you?
From sciencelearn.org, the atoms and molecules in gases are much more spread out than in solids or liquids. They vibrate and move freely at high speeds. A gas will fill any container, but if the container is not sealed, the gas will escape. Will. Because you can temporarily put some gas pressure inside an open container. Temporarily. Because what's going to happen, it's going to increase entropy and it will escape.
Have you ever noticed how John never puts his citations on the screen? He just shows a link to them. It's almost like he doesn't want you to see something, isn't it? This was the one he just put up. It actually surprised me a little bit because this is clearly intended for middle school age kids, and it's talking about water, but that's okay. Water can be a gas. So let's see if we can find what John was talking about. Here we go. Gas. This is what he read. The atoms and molecules in gases are much more spread out than in solids or liquids. They vibrate and move freely at high speeds. A gas will fill any container, but if the container is not sealed, the gas will escape. You stopped there, John. You didn't read this next part. Let's try this. Gas can be compressed much more easily than a liquid or a solid. Think about a diving tank. 600 liters of gas is compressed into a 3-liter cylinder. Now we're talking about compressed gas, John. And nowhere in here does it talk about how long it's going to take that gas to leave that compressed cylinder. Do you see that anywhere? What, were you just making that up? I'll tell you what, maybe this will help you understand. Entropy, you say, John? Here's your old friend the pipe. This time the pipe has got air in it. The pipe's pressurized to about 2.3 inches water gauge. That's just air pressure. Now according to you, the pressure will stick around for a while as entropy takes over. That's what I heard you say. What happens when I open this valve? Uh-oh. The pressure went away immediately, John. Now what do you think could have happened? You know, I wonder why the butane stayed in that pipe. I've got an idea. I'll bet it was the weight of the atmosphere above it pressing down on it.
Let's define will.
No, Whistledick. Don't define will. Let's move on to some more cherry picking.
My word. Here's NASA's take on gas pressure. The molecules are in constant random motion and frequently collide with each other and the walls of the container. Because the molecules are in motion, a gas will expand to fill the container. Since the density is defined to be the mass divided by the volume, density depends directly on the size of the container in which a fixed mass of gas is confined. They're even telling you, you're priests.
Oh my goodness, we have another cherry pick by Quantum Eraser. Here's the NASA paper that you quoted, John. Let's see, forget that you started in the middle of the sentence where you were leaving out intentionally the part about kinetic theory. That's okay, we'll let you get away with that. This is what you read. A gas is composed of a large number of molecules that are very small relative to the distance between the molecules, and so forth and so on. I won't go through the whole thing. What you didn't read, though, was this down here in this last paragraph. These rather simple examples help explain a fundamental effect that we see in nature between cases 3 and 4. The number of molecules in a given volume decreased and the corresponding density decreased. In the atmosphere, air molecules near the surface of the Earth are held together more tightly than the molecules in the higher atmosphere because of the gravitational pull of the Earth on all the molecules above the surface molecules. The higher up you go in the atmosphere, the fewer the molecules there are above you, and the lower the confining force. So in the atmosphere, density decreases as you increase altitude. There are fewer molecules. Why did you leave that out?
Again, from Elmhurst University Chemistry Department, the pressure of a gas is the force the gas exerts on the walls of its container.
This is not looking good, Whistledook. From Elmhurst University, what you quoted was just this one little sentence. The pressure of a gas is the force that gas exerts on the walls of its container. You seem to have omitted this paragraph. I wonder why. Let's see. Atmospheric pressure varies with height just as water pressure varies with depth. As a swimmer dives deeper, the water pressure increases. As a mountain climber ascends to higher altitudes, the atmospheric pressure decreases. His body is compressed by a smaller amount of air above it. The atmospheric pressure at 20,000 feet is only 1/2 that at sea level because about half of the entire atmosphere is below this elevation. Wow, John, I think I see a pattern developing.
Kinetic molecular theory explanation of Boyle's gas law. Observations about pressure may be explained using the following ideas. The rapid motion and collisions of molecules with the walls of the container causes pressure, force on a unit area. Pressure is proportional to the number of molecular collisions and the force of the collisions in a particular area. The more collisions of gas molecules with what? The walls, the higher the pressure.
That's the same citation from Elmhurst University. This time you whistled past the atmospheric pressure description and skipped down to kinetic molecular theory and the explanation of Boyle's law.
And for Ken Lieber text, pressure is caused, again, by gas molecules hitting what? The walls of the container. With a smaller volume, the gas molecules will hit the walls more frequently, and so the pressure increases.
This is starting to become boring, Huey. This time you're talking about Boyle's law, and Boyle's law simply relates the pressure and volume of a fixed mass of gas at a constant temperature. The part I highlighted is the part you selected. Let's read the whole thing, though. Simple explanation. This is easiest to see if you think about the effect of decreasing the volume of a fixed mass of gas at a constant temperature. Pressure is caused by gas molecules hitting the walls of the container. With a smaller volume, the gas molecules will hit the walls more frequently, and so pressure increases. You might argue that this isn't actually what Boyle's law says. It wants you to increase the pressure first and see what effect that has on the volume. But in fact, it amounts to the same thing. If you want to increase the pressure of a fixed mass of gas without changing the temperature, the only way you can do it is to squeeze it into a smaller volume. That causes the molecules to hit the walls more often, and so the pressure increases. Now, QE, what this would apply to is my pipe if I sealed it. If I sealed that 4-foot pipe, filled it with a mass of gas, and then forced that gas into a volume of a 2-foot pipe, I would double the pressure. That's all this says. And it has nothing to do with atmospheric pressure whatsoever. But the same source, Chem Lieber text, also provides a section on gas pressure. And in that section, they describe the pressure of a gas as being the force that the gas exerts on the walls of its container. And of course, that's the kinetic molecular theory. But then they go on to describe atmospheric pressure. And if you read this paragraph, you will find that it is word for word identical to the description provided by Elmhurst University. Now, QE, it doesn't appear that anyone agrees with you that gas pressure and atmospheric pressure are the same. What do you got to say about that?
So the necessary antecedents that cause gas pressure, the things that cause it, are the rapid motion and collision of molecules. Well, collisions with what? Well, with the walls of the container.
Well, QE, since you insist on whistling past the obvious difference in atmospheric pressure and gas pressure, let me give you a citation of my own. This comes from lumenlearning.com. You've used these guys too. Read right here. Atmospheric pressure is a measure of absolute pressure and is due to the weight of the air molecules above a certain height relative to sea level, increasing with decreasing altitude and decreasing with increasing altitude. Go down to this lower paragraph. Atmospheric pressure is due to the force of the molecules in the atmosphere and is a case of hydrostatic pressure. Depending on the altitude relative to sea level, the actual atmospheric pressure will be less at higher altitudes and more at lower altitudes as the weight of the air molecules in the immediate atmosphere changes, thus changing the effective atmospheric pressure. The pressure of a fixed mass of gas at a constant temperature is strictly dependent on the volume of the container holding the gas. If you decrease the volume of the container, you will increase the pressure. If you increase the volume, you will decrease the pressure. Atmospheric pressure has nothing to do with volume. Atmospheric pressure is a result of the weight of the atmosphere above you. That weight is determined by the acceleration of gravity. Get over it, you crotch waffle.
This is quite elementary. Take either one or two away and you don't have gas pressure. Simple. No amount of linguistics or mathematical acrobatics is going to change it. Newsflash, you can't have volume without a container.
Now Quantum Eraser is going to try to tell us that a cup of flour is only a cup of flour while it's still in the measuring cup. If you pour it on the countertop, it no longer has any volume because it's not in a container. You know, that's a level of stupid I can't even relate to. We just saw 5 consecutive citations and 5 consecutive cherry picks from QE. And we just showed how easily we could debunk each and every one of them with QE's own citations. I think that'll do. Hey, thanks for watching. I hope you guys enjoyed it. There'll be more of these. Remember, QE, when I say how stupid can you be, that isn't a challenge. That's a question. Hey, don't forget to hit those like and subscribe buttons down there. Doesn't matter which one. Hit any of them. And if you press that little bell, it'll give you notifications the next time we have a video. There's a link to the Patreon. That'll be up in the description. And with that, we'll see you guys on the next one.
Are we understanding each other? You're an